either now tuning the frequency, so or the Rabl frequency, I can make one of these transitions resonant. Okay, so is this anything unclear? I mean, it's really something, if you start, I mean, from a two-level system, you're probably familiar with this kind of rest state. The two-level system here is just a generalization to these three levels. Okay, so this of course now helps us, to make essentially, if this detuning or these energy differences are now order of mechanical frequency, you have again resonant processes. So, but I think the second and equally important effect comes now if I look at again at this nuclear spin path. And you can, the first approximation you can always think about, say, the bare and V center, and then there are some fields which produce this B field coupling this to SC. And this, this B field, again, it's very, very slowly varying, but it's random. So over time, or each time you do the experiment, you get a different value, and this is actually very high. So if I look now, if I'm now close to omega 0, so if I'm omega on, but very small, simply this plus minus 1 state, if I have a random shift here, or a delta n, they will simply linearly follow the shift. And if each time I decide this transition here, each time I do the experiment, in general, it will be highly out of resonance. Okay, so but if I now add my driving field, and I increase the strong driving field, so make this tuning in omega almost equal, what I find is that I now get these hyperclasters, so these stress states. Okay? And they depend on this delta only in a quadratic way. Okay? So I've smoothed out this, so if now this delta changes a little bit, then the effect is suppressed. It's only quadratic. So the thing now, so this would also work for a two-level system. I think the nice feature about this NV center, this three-level configuration, is that if you look at this state up here, so this start state and the ground state, and tune these parameters, you actually find a situation where this curvature and this curvature are also the same. Okay? So this means for this transition, also the quadratic effect vanishes, and you're left with something which is fourth order. Okay, so this kind of now summarize how actually, starting with something which isn't a strong coupling regime, but very very bad type of interaction, by applying these microwave fields and making this symmetric combination, I end up now in this type of James Cummings model and these three states. I can tune my transition frequency or my effective splitting between these states to be resonant with my mechanics, so the achieve resonant interaction. At the same time, I suppress dephasing effects, and in the end, I do something like you could call a continuous spin, so it's constantly up and down state. And if I now express my model, original model, describing this effective James Cummings model in terms of these operators, I get a small loss of my coupling strength, but it's only kind of a square root of 2 effect. Okay, so I don't really lose anything in this. So this kind of now so once you're at this stage, now you can go back and do what we discussed in the first lecture. You can use this exchange together with optical bumping to achieve cooling, or you can do it now because you have strong coupling. You can do great spin superposition, swap it on the phonon, and then do it back and do the spin detection. Okay, all these techniques I described in the first lecture. But I think the main important thing is really, how in this solid state environment, how do we actually optimize the air interaction to something which is really optimal even under these conditions with all the dephasing and everything. Okay, and that's the main message. So this were now kind of two examples how we can use either electrics or superconducting qubits, or surprisingly even spin qubits, to couple strongly to the motion of this oscillator and maybe do something, use it for ground state cooling, use it to prepare superposition state, and maybe do some principal tests of quantum mechanics with these systems. But now let me go to this question, what to actually do, what do we want to do it for? Maybe people will ask you this stage, and you say, put resonators to ground state. And the next question is, yeah, what do you do with it? You say, okay, prepare superpositions. Next question, what do you do with it? Okay. What is it good for? Why should I put money into this? And here's, I think, kind of a very basic, but I think very illustrated idea where this field really can go eventually. And this is now this, let me just again describe this. What do I mean by mechanical quantum transducers? And okay, so to motivate the following, I will again look at these electronic spin qubits. And I know I mentioned in these centers before, but people also use force photons and different types of qubits. Why do you want to use them as qubits? Well, I can put them in the solids, they stay there, so it's really easy to scale up. And they have very weak magnetic dipole interaction, so they're very isolated from the environment. And this really gives this huge coherence times even at room temperature. Okay, so that's very interesting, and that's why many people are excited about these systems. But now, if you look back, I mean, eventually, if you do something quantum computing, you also want to have them interact. Okay, and now this weak magnetic dipole interaction, of course, hurts you. Okay? Especially if you want to do reasonable gate operations, you have to place these two spins in the order of kind of 10 nanometers apart. Okay? And there are some first experiments which demonstrate this. This is a very random process. You look at all types of NP centers, eventually find two very close. So this can be done, and there's some ideas maybe to make it more deterministic. But this is, I think, really at the moment a gauge stopper in this field, or something which takes a while to work on. So how can mechanical systems help to overcome this problem? Okay, so let's me again look at this, mechanical beam, that tip, and couple to a spin qubit. Okay, one way to think about this coupling again is that there's a spin-dependent force, so depending if the spin is aligned in this direction or this direction, the mechanical oscillator will be placed in this direction or in this direction. Okay, so the spin superposition again is translated displacement superposition. So, but now this is a macroscopic object, and so what I can do now is I can put maybe a gate electrode on this resonator and charge it up. Okay. So then what happens is that this displacement I created before translates in electric dipole. And now electric interactions are very, very strong. So let's put this same thing, second dipole here. And so in both cases, the spin dipole moment is converted into displacement and then converted into electric dipole moment. And effectively, this makes the two spins interact via strong electric dipole interactions. Here is kind of the basic idea. You can be a little bit more specific. I mean, how would you do it in practice? Okay, so this direct interaction, it would work over a certain distance. But what you can also do is, you couple two resonators. You put capacitance here, capacitance there, connect them by a wire, and you actually find that so there's effective interaction, which of course decreases as the wire gets longer and longer. But if you put in some realistic values about distances of 100 micrometers, you find that this effective interaction here can still be in the order of 100 kilohertz, maybe even more. So this means the type of interactions I get by direct magnetic interaction on a 10 nanometer scale, I now get by making use of this transducer on a 100 micrometer scale. Okay? And this kind of illustrates why this amplification kind of can really be useful. So now having kind of this basic mechanism, I can of course put in many resonators, connect them by strings or wires. In this case, I get also get again this coupled resonator chain. I can express this in collective Phonon modes, and in the end, I put everything together. I kind of get this kind of typical systems. I have my individual qubits, which I now can control because they're far separated. I get my collective Phonon modes as a quantum bus, and the page of the qubits is coupled to these Phonon modes. And because that is collective Phonon modes, I now know you can do effective spin-speed couplings. And in this sense, now kind of back to the title of first lectures, in this sense, these mechanical resonators really have the role now of really big, massive ions. Okay, so kind of, okay, this is the analogy. So just let me very briefly point out, I mean, what is maybe now the difference, or what can we do with it? How do we treat the system? And let me again look at this now this simple form of basic form of this Hamiltonian. So this is qubit control, which I just neglect for the moment. And I have my resonators, and I have the spins coupled to my resonators. All these coupling constants depending on my own functions.
If there's a large field gradient for the interaction, what about the static field from the resonator? Causing so much?
Yeah, so this is depends. So the thing is, so I mean the scheme so the one hand, the tip of the resonator produces a B field, and in principle it just creates a splitting between these two states. So if I'm interested now again in a scheme where I only address these two, I mean forget about this three-level configuration, but just these states. I mean I just want that this external B field created by the tip is not too large to completely destroy this level structure. And I mean, if the tip field, it's very large, I mean, I can think about applying a compensation field, which then, of course, also would push the resonator up a little bit. I don't have really, top of my head now, a number, how much fields, what is the effect. But in principle, it's also not really crucial to compensate this effect. And in the end of the day, you maybe want to go to double clamped oscillators, which, okay, put a B field, it will stretch the oscillator, but it doesn't do damage. I mean, the single clamped oscillators can be very floppy, and you might be careful, but anything that's double clamped should be okay. Okay, so let me again look at this Hamiltonian. So we have a bunch of Phonon modes, and we have now these spins coupled in a general way to these Phonon modes. And at the end of last lecture, I kind of wrote down kind of a similar Hamiltonian, and I told you about these geometric gates. I mean, once I can time-dependently drive these numbers, okay, I can use this Hamiltonian to implement arbitrary spin-spin interactions. So maybe another way to look at this is, or anybody coming from solid state or condensed matter physics would do with such a Hamiltonian, they would apply a Phonon transformation. And what this Phonon transformation is just written here does, it gets kind of rid of this direct interaction and converts my Hamiltonian into something which is just a free Phonon Hamiltonian, should this will remain. It will cancel this linear interaction, and you're left with something which is now quadratic in the spin-spin interaction. And these coupling matrix elements between the spins, they are now a function of all these Phonon mode functions and Phonon frequencies over here. And maybe so, this just point out, I mean, it's a very useful transformation. If you don't understand what's going on here, let me just briefly explain it in pictures. So first of all, think about just a normal single oscillator coupled to a spin-dependent force. Okay, what you can do in kind of if you don't have time-dependent forces, you might think about the system as an oscillator which has a force which acting on spin state, so it's either acting up or down. So oscillator with a force, is again an oscillator, but a displaced oscillator. And what I did with this transformation, with this displaced oscillator basis, I redefined the oscillator position if the qubit is in state up to minus theta, and if it's in state down to plus theta. Okay? So these are now my new basis states. Whenever I change my spin state, I consider the oscillator being at the new equilibrium position. And if I now do this for two oscillators, I get kind of this configuration. So displaced by depending on the spin, they're sitting either displaced to the left or to the right. And if I now switch on some coupling between them, you see that these two states will feel a strong interaction than these two states. And that's what leads now to this effective spin-spin interaction. This kind of now another way to compare to this time-dependent formulas that we had yesterday. This kind of another way to think about this interaction. So in the end, okay, so I can now do this, and okay, so this is now just a general slide. So simply to say that something which I cannot do in trapped ions is, so this again starting from this interaction, I have here all my so the coupling between the mechanical systems, which I can design. Okay, I can wire these resonators up whenever I want. And depending how I design these couplings, I end up with different spin models. So this also not only allows me to amplify my interactions to larger distances, but also kind of use all the fabrication techniques or control we have over electric circuits and map them on the spins. So this is kind of also a nice way. And I think so at this stage, of course, one would have to tell you a lot about how I charge up my resonator, so there will be electric field noise or all type of noises. It is now a little bit longer discussion. I mean, we have done now all the analysis, and of course there's this one over F noise and so on, so there's it's not so trivial, but in the end, if you put in all the numbers, I think it really turns out that these type of interactions should still prevail over the usually expected system. So, but okay, so I'm kind of at the end of my talk, so just let me briefly summarize kind of the main messages. And kind of the first one is, okay, so if we want to manipulate these mechanical systems, so this coupling to microscopic, especially solid state systems, I mean, there have been many works along these things, and this is now, I think, at the moment still very much on the theory side, but there are also first experiments going this direction. And I think there are many candidates to achieve these strong coupling conditions, but you should also keep in mind that, in the solid state systems, there's always low frequency noise around, there's always off-resonant conditions. So in each case, you actually might think about how to correctly apply driving field control devices to an echo scheme to make it actually realistic in the system. And I briefly, pointed out two ideas, both for the charge qubit and spin qubits, which maybe, of course for you at some other stage you might encounter similar problems, might be helpful. So kind of the second message is now, okay, so here is just kind of coupling two systems, I mean, doing quantum stuff, some really nice fundamental physics with macroscopic objects. You want to see, I mean, where does this field maybe go to in the future. I really want to again point out that this ability for this mechanical system, and I think in this sense it's really unique, and it can really couple to all types of forces in our system. And now if we bring this interaction also to the quantum regime, this could really be a quite universal mechanism to communicate between different quantum systems. And as an illustration, really I pointed out this spin transducer here, but you can also extend the scheme and add optical elements, also historical microwave cavities, to maybe also convert spin qubits or charge qubits to really create optical interfaces, to not only go over 100 micrometers, but over long distance communication. And of course, okay, again, these ideas, I mean, they are very preliminary, theorist point of view. I mean, John and other guys are thinking now about how to actually do this in a more realistic way, and quite confident that actually these things eventually will happen in this field. And as final comment, so this was more like now a little bit a review of what I've been done and doing, and also what other people have been doing over the past years in this context. Just as an outlook, I want to say that at the moment we are working on a slightly different variation of this NV center coupled to resonators, where the NV center is not magnetically coupled, but embedded in a diamond nanobeam. This creates then a strong strain coupling in the excited state. We're currently working out some scheme, how can we actually use this to do some cooling effects of this diamond resonant beam, but also how can we use this strain coupling to do effective qubit-qubit or spin-spin interactions or collective spin interactions in such a nanobeam, and maybe use it for spin-squeezing and these type of things. And if you have questions, and maybe time later, I'm happy to explain it more. Okay, I think that's
Thank you very much.